So we'll be looking at the graphical representation of a strong acid against a strong base titration in conductometric titration. A strong acid against a strong base. Now looking at HCl, which is a strong acid, and NaOH, which is a strong base. Now in this titration, the HCl is acting as the analyte. HCl is acting as the analyte, and the NaOH is acting as the titrant. The HCl is acting as the analyte, that's a solution of known concentration, and the NaOH is acting as the titrant, that is the solution of unknown concentration. And this is the titrant, solution of known concentration. Now, the titrants, we keep on adding the titrant to the analyte, and there'll be a change in conductivity as we keep on adding. So, we want to depict what this graph mean, the stages of this graph, 1, 2, 3, 4, what they actually mean. So, and if you're plotting your graph of your conductometric graph, you should note that you have your conductivity against volume of titrants, which is NOH, or whatever solution it might be. So it goes your conductivity against the volume of titrants, conductivity in the y-axis, and your volume of titrants in the x-axis. Now we'll be detecting what all these points, we'll be interpreting what these points mean. Now at point 1, that's before the addition of NaOH, before NaOH was added at this point 1, you are only left with your HCl at point 1. When you've not added NaOH, that's NaOH, volume should be 0 around here as your point 1. The volume will be 0. You've not added any sodium hydroxide. There will be an ionization. This HCl will ionize to form H plus Cl minus. There will be an ionization that produces H plus and Cl minus, because the solution is only made up of HCl at point 1. NaOH is not added yet. It's only made up of HCl, and this HCl will ionize to hydrogen ion and chloride ion, producing H ion and chloride ion. Now, because as we've said about the mass of ion connecting with the conductivity, or connecting with the conductivity of the solution, now because H plus has a lower mass compared to chloride ion, this will have the highest conductivity. So this gives the solution a very high conductivity because of the H plus in the solution. It gives it a very high conductivity. That's the dominant ion, is a dominant ion in the solution. Now, you see the H plus is highly mobile, which interprets to a high conductivity at the beginning of the experiment. So why the experiment has a very high conductivity at the beginning of the experiment is because of the H plus in the HCl, which ionizes to H plus and Cl minus. But after the ionization, we find out that H plus, that's hydrogen ion or proton ion, has a very low mass and confers a very high conductivity as compared to, say, chloride ion. So this gives it a very high conductivity. Then at point 2, as NaOH is being added, now we should know that at point 2, you can call this point the pre-equivalent point. Point 2 is the pre-equivalent point. That's when we start adding our NaOH to the solution. Now, as point 2, as NaOH is being added, some of the mobile H plus will be replaced by NaOH. Now, yeah, remember the reaction between HCl and NaOH. It needs to form a salt and water. Now, as we keep on adding NaOH, the hydrogen ion in the solution will keep on reducing because they'll tend to form water, and the sodium ion will replace it. Sodium ion will replace the hydrogen ion with chloride ion to form salt. So that what it means. At point 2, that's at pre-equivalent point, as we keep on adding NaOH, as NaOH is being added, some of the mobile H plus will be replaced by Na plus, and this will lead to a decrease in conductivity. Why? Because after you've replaced, if this is HCl being replaced to NaCl, and we have H plus and Cl minus and Na plus and Cl minus. Comparing H and Na plus. Remember, we said the higher the mass of the ion, lower the conductivity. So as we are removing H plus from the solution and replacing it with a higher aeon, we see that this conductivity of the solution will start reduced because sodium aeon has a lower conductivity compared to hydrogen aeon. So it will lead to a decrease in conductivity until equivalent point is reached. So this is what we see here, that at this point too, the solution keeps on, the conductivity of the solution keeps on decreasing until we get to the equivalent point, because at this point, in a equivalent point, the hydrogen ion is being replaced by the sodium ion from the sodium hydroxide. Now at point 3, now we should know that at point 3, this will call the equivalent point. Point 3 is the equivalent point. So at point 3, equivalent point is reached. The curve experiences a sharp or acute turn. Now you can see that there is an acute turn in the curve. There's an acute turn. The curve turns in an acute way. And we should try to remember that the more acute the turn is, the more accurate the titration. Allow me to write it here. The more acute the turn is, the more accurate or less error in the reaction. So the more acute the more acute the turn is, the more accurate or the less error that we have in the titration. But the more obtuse, the opposite of obtuse is obtuse angle, of acute angle is obtuse. Acute angle, if you can remember from our geometry, this is an acute angle, this is an obtuse angle. So it keeps on going wider. So if this equation, if this graph confers a obtuse, gives a obtuse shape compared to this, for a strong acid strong base, it tells you that this is more correct. Than this. As a person having this shape and a person having this shape, this is more correct than the person having this. This is more accurate, giving a less error for the titration than this. So at theory, equivalent point is reached. The curve experiences a sharp, we've talked about the sharp acute turn. It should also be noted that at equivalent point, all the hydrogen ion, we should note that all the hydrogen ion from HCl has been exhausted. Remember, I told you we've done the equation. This replaces this, then the hydrogen ion reacts with hydroxide ion to form water. This is what it depicts it here. Hydrogen ion reacts with hydroxide ion to form water. So all the H plus will be replaced by NaOH plus, and the H plus reacts with the hydroxide ion to form water. So that makes it stop at this point. It stops at this point because there's no more H plus in the reaction. Now going to 4. At point 4, OH takes over. That's the hydroxyl ion. The hydroxyl ion takes over the conductivity, because Na we keep on reacting with chloride ions to form salts, but the OH now takes over the conductivity, being also a lower ion. It keeps on rising, and this tells us that the reaction takes over the conductivity as Na remains as salt, as forming NaCl, and the solution becomes basic because OH confers basicity to the solution. So the conductivity of the solution keeps on rising as we keep on adding titrants, and this tells us that this 4 is the post equivalent point. So I would